Here on my workbench I have a Panasonic, this is a Pro line monitor. I used to use this in my studio. It says Texas Instruments on here, but it's actually Panasonic. Now this monitor was sold as part of Texas Instruments' venture into home computing when they had the TI-99/4A. For those of you not old enough to remember that computer, because that goes back to about 1980, that was the computer that Bill Cosby used to flog. It sold for, I think it was $400, $400 or $500, had 16K, not 16 megs, 16 kilobytes of RAM, a 1 megahertz processor, and you plug these cartridges in like a game console. You could get games, but you could also program it. It had TI Basic built in. You could get a extended basic cartridge for it that would give you access to, say, disk drives and stuff. Out of the box, the thing used a cassette tape to store and retrieve programs. All out, if you bought the whole system, if you bought the console and the expansion pack, which would allow you to put up to 4 disk drive units. Actually, the initial controller card would let you support just 2 single density, single-sided diskette drives, but an aftermarket controller came out that would allow you to put double density. Now we're talking 360 kilobytes per 5¼ inch floppy. There's a lot of storage back then though, right? And the expansion memory would let you add 48 kilobytes of RAM to it. This whole little computer system, if you hit the whole shooting match, would run you around $1,200. I have such a system. My first computer that I learned to program on back in 1980 or 81 was a Texas Instruments TI-99/4A. I still have the computer. I never bought the monitor though for it, because this monitor was like $799 for this monitor, maybe even more. This was more money than the computer cost. Everybody else, we just used the RF modulator that came with it that put the crappy 40 character display onto a regular TV. But they did have this real nice monitor that was part of the setup, and this is it. This was given to me several years ago by an old friend, by actually the widow of an old friend, a guy that I had shot his wedding for him. I guess it would have been probably early 80s, I guess. And he was a taxi driver, and somebody murdered him, shot him in a robbery. And his widow knew that I had a Texas Instruments computer system, so when she was getting rid of his stuff, she called me up and she said, "Hey, how would you like this monitor?" And I said, "Sure." So it was an old friend that we were part of the TI-99 computer users group after Texas Instruments abandoned us. They orphaned us. All the users that had them, we kind of formed our own little group, and we all wrote programs and shared them and stuff. And back in the BBS days, I actually had a bulletin board that was running using the Texas Instruments computer, the TI-99. Anyway, I used this monitor in my studio for a while. It has a fantastic picture, but it's got a problem. It's dead. So we're going to crack this sucker open. I'm going to fix this monitor, and then this monitor is going to go up there to replace this little 8-inch Sony, because I think this one's got a real nice picture, and I like to get some use out of it. So let's get this thing apart and see why it's not working. Being a professional monitor, it's got a metal case. This is something that consumer equipment just didn't have, and that is probably one of the reasons why these things were so darn expensive. Now, under the Panasonic badge, when I was first setting up my edit suite, I could have bought one of these with the Panasonic name on it, but they were ridiculously expensive, like over $1,000 for this particular monitor. It was just, it's stupid. I mean, really, there's nothing in here that makes it anything more special than a TV, other than the fact that, well, it is a little higher resolution. Well, you'll see, it's got a lot of shielding in here that TVs didn't have. But let's get the thing apart. There you go. Made in Japan. Matsushita Electric Industrial Co. December 1982 is the build date on this unit. So this monitor features the dumb monitor design. When the cabinet is removed, if you set it down to work on it, the bottom will actually flex in and could make contact with the circuit board, causing major sparks. So we'll just remove the base plate to remove any chance of that happening. This monitor uses the 290KB22. It's an inline gun color high resolution CRT. This actually is quite a high resolution tube, made in Japan, very good quality, and when this set's running, it does have a spectacular picture. It's got full magnetic shielding, as would be expected from all broadcast and industrial monitors. They actually magnetically shield the yoke so that the Earth's magnetic field doesn't influence the picture. And that's one of the big problems with analog monitors, consumer grade, is that they don't shield the yokes. So you turn a monitor around and the purity will change. And the Earth magnetic field will interfere, or can interfere, with the picture geometry and picture purity. That's not generally a problem with industrial grade and broadcast monitors because they're all shielded. And this is also not only for shielding from magnetic, but this is also part of the X-ray shielding that prevents, because these type of monitors are designed for people working close to them for hours at a time. Like, for example, this was actually part of an editing bay package that Panasonic had. Their industrial 3/4 inch editing machines of the day. So you'd have an editor that would be sitting in front of these monitors within a couple feet for 8-10 hours a day. So this extra shielding was there to protect the user who's going to be sitting in front of it, or if it's being used for security cameras and you've got someone watching it all day long. CRTs, cathode ray tubes, can emit X-rays, especially the higher resolution tubes, because they generally tend to run the high voltage higher on these industrial sets than a consumer set. Higher voltage means more X-rays can be produced. So you want to shield these tubes to prevent those X-rays from getting out and becoming a problem. And that's why all this extra shielding and the metal cabinet. On the right side of this television, we're going to have the horizontal output. There's a shield on here because there is high voltage on this transistor when it's energized. And this is going to be our B+ regulator. So the first place we're going to start is we want to see whether we've got our B+. I'm plugging this into an isolation transformer because it is a hot chassis. When you're working on hot chassis, you want to make sure that you're isolated from AC power, because this whole chassis could end up becoming live. So I'm plugged into an isolation bar, or isolation transformer. My power bar here is on an isolation transformer, and it's on my Variac. So now let's just check some voltage measurements and see whether we have our raw B+. We've got our meter set up. I've got my ground, my negative terminal is connected to just the metal chassis here. I'm going to measure for my raw B+. My raw B+ should probably be between 160 and 170 volts. This is the unregulated, so direct from the AC line, this should be my B+ for the set. So if I put my probe on, turn on the power, we'll put the probe on here, and we'll find that we actually have 170 volts, 169.9, 170 volts. That's close enough for me. The next thing we want to determine is, do we have horizontal? Is our horizontal circuit operating? For that, I'm not going to put my meter on here, because if it is running, it's going to have about 1,000 volt pulse on it, and that'll blow my meter up. So for that, I'm going to use my scope with my ×10 probe. On my probe, I'm going to select the ×10 input, because that way I can measure a much higher voltage than the scope could normally handle. Scope is good for, I think it's 600 volts, so this will give me a ×10. I can go well over 1,000 volts with this thing. And what we'll do is we'll just swing over to the scope here. I'm just going to turn down my divisions, turn it all the way down to like 10 volts per division, because that now becomes 100 volts per division. We'll set it up for channel 1, and we'll just kind of center it here. And again, the same thing, I'm going to ground my probe, and we'll just measure and see whether we have anything on the horizontal output. I'll make sure the set is off first. I'll pull the shield back out of the way here so that I can access the transistor. So this is going to have the high voltage on it if the set is running. So I'll put my probe on the collector, which is the case, and turn the set on. And we saw something there initially, but it didn't run for very long. It shut off right away. So let's turn it off and watch the scope. Something initially for a second there. I don't know if I saw any waveform there, or whether that was just the DC voltage coming up. No, that's just the DC voltage. So we don't have it, our oscillator's not running. So I can, for that matter, now that I know it's just the DC voltage on there, I could put my meter on there and check it, because there is no 1000 volt pulse there. It's just, oh, there was a little bit there though when I first turned it on. It tried to start. I don't know if you noticed that on the scope here at all, but when it first kicked, I saw some oscillation, and then it shut off. We'll try it again. You'll watch the scope. See, just a little bit there. I know that the trace went off the screen because of the DC offset, but there was definitely some drive there. If we speed up the scope here, might even be able to see a pulse. There, see the pulse there, and then it went off. We'll just bring our time base back here a bit and see if we can catch it again. Got to let this thing completely discharge. So it's going into shutdown. It's trying to start, and it's going into shutdown mode. So we'll try that again. See, the pulse is there, and then they shut off. So the set is trying to start up. For some reason it's going into shutdown. We have a component that's failed or something. Or the voltage is too high and it's going into over voltage shutdown. First thing we can try is lower the B+. If we lower down the B+, in case it's a regulator problem with the variac, we'll see if the set actually starts up this time. Ah, it stayed on for a bit, but then I heard my power bar kick out. I have a power bar here that's got it's got over and under voltage on it, so if the voltage is too low, it'll actually shut off. I may have to plug the TV directly into the variac. So it tried to start there for a second. Let's just plug the TV directly into the variac and not into my power bar, just because my power bar itself, I'm going to have to take this power bar apart and jump her over the relay that's on there. It's one of these power bars that's got over voltage and under voltage protection, and if I turn my voltage down too low, if I turn it down below, I think it's 85 volts, it'll shut off, or 90 volts, it'll shut off. If I turn it above 120, it'll shut off, or 130. It's one of these stupid smart power bars that is too smart for its own good, at least when it's used in this environment. Okay, we'll try powering this thing up again. This time I'm going to try it up at about 80 volts and see whether this set will stay running. Okay, so we have horizontal here. We have horizontal pulse. We got lots of signal here. I'm just going to uncalibrate my probe here, because we got over 1,000 volts here. And we actually have a raster on the screen, a bright white raster on the screen right now. So we know that the set is actually running. I'll show it to you. We'll turn it around here. So you'll see the screen's going to light up here. You see? Actually, that's not good. It's too bright. If I bring the voltage down a bit, if I bring the voltage up, it's going to probably go into shutdown mode here. There, it's going into shutdown. And it's shutting down when I get my input voltage up to about 85 volts. So what we've got on here is we've got a regulation problem. The regulator transistor is not regulating my raw B+, so my B+ is too high, which means my high voltage is going to be too high. if my high voltage is going to be too high, this picture tube is going to start spewing out X-rays, so the over voltage protection shuts the set down so that it doesn't spew out X-rays. So what we need to do is we need to find out why the regulator on here is not working. But we know our horizontal deflection works and our vertical deflection works, and we have a bright white screen because there's a fault somewhere in the power supply. And now it's just a point of figuring out where that problem is. But I know where to start. I know that I have to start in the power supply, the regulator circuit. Here's a clue as to what my B plus is supposed to be. It's a 116 volt adjustment here, a little trimmer, which tells me that that regulator, when it's working, is supposed to be regulating down at 116 volts. So this gives me a clue to where to start. We have our regulation circuit here. There'll be a couple of resistors in here. Could be one of these could be open. Something's causing my regulator not to work. But now we've got a clue as to where to start working. Televisions and monitors such as this use what's called a shunt regulator. So there's typically going to be a big resistor like this one right here. This is going to be our shunt regulator resistor. And basically the transistor doesn't pass all of the current. Most of the current passes through the resistor. So we'll find that if we look at the leads from this big resistor here, one's going to go down to the collector, which is this green one here. That's the input. That's the raw B plus there. So if I clip on here, I'll see the same voltage as I see on the collector of that output transistor. The emitter line, which is going to be the regulator side, goes to this side of the resistor. Now ideally, if I were to disconnect this line completely here, bypass that transistor, all the current would be going through this resistor and we would have a low voltage situation. How it works is the majority of the voltage goes through this resistor. This is the 270 ohm resistor, 10 watt. So the majority of the operating current for the set goes through that resistor. It also goes through this other resistor as well, but this is a 12 ohm. This is more of a fusible resistor, this one. If I'm thinking right, this one's probably the main surge resistor, this one. So everything goes through this resistor, and I bet you if I trace this wire back, this is going to go back to the rectifier, to the main filter, if I were to trace that wire back. Because it looks to be that the B plus comes in, and it goes through this resistor, and then it goes from here down to the regulator. It goes from here, this green wire is the reference, and this green wire here goes down to the collector. I don't know where this green wire goes, it goes somewhere else. The purple wires go to the TV. This is the B plus here on this line, and it also goes down to the emitter right down here. So if I power this set up now, this should be my regulated B plus, but it's not going to be because the regulator's not working. But let's just turn on the set. Power's on there. We'll just turn on the set here and we'll see that it's going up. It's 109 volts, 110 volts. The set's working now, right? The set will be on because I've got my input voltage down at, what am I at here? I'm at about 80 volts and my screen is lit. If I look at this side, I got 113 volts. So my regulator is not working at all. As I increase the voltage, when this thing goes up beyond 113 volts, it should shut down. Okay, the set should go into shutdown now. It's gone up to 128 and the set is shut down. We'll find that because there's no load, it's going to be virtually the same. 136 on one side, 128 on the other. So this regulator transistor is not regulating. Either the transistor itself is blown or the regulation circuit has gone open down here. Let's take a look at the regulation circuit. Let's trace that wire back and see where it goes. It's going to go down to this pot here, for sure. Whoops, can't see what I'm doing. It's going to go down here somewhere into this pot. Let's trace that wire. We're going to trace the, I think it's the red wire. Yeah, the red wire off the base of the regulator transistor. This is the control for that transistor. Let's see where it goes. See, this is fun because I don't have a schematic, so I basically have to reverse engineer this in my head because I don't have a print for this set. So what you're seeing here is me figuring out what the engineer did to make the set work. When you've got a schematic, it's one thing. You can see exactly how the circuit is wired. You know exactly what they're doing because you can see the layout. If you don't have a schematic, it becomes much more difficult because you actually have to trace wires to see where they go, look at where they go on the circuit board, and then try to figure out what they've done. But I'm pretty confident that I'll figure this out, and it won't take me that long. Our wire is going from our base. It's coming right down here to this wire wrap here, right behind the fuse. So I'm going to turn the board over and we'll see where it goes from there. Here's our test stake here, A17, right here. That's the wire that goes to the base of our transistor. So I'm going to look at the circuit and see where it goes. Chances are it's going to go to a couple of resistors that divide it off of this 116 volt adjustment. Of course, you know what they say, right? Never overlook the obvious. Maybe, just maybe, that because it's been sitting for a while, that control has gotten dirty. So I moved the control a bit and I have control. We'll set our voltage to 113 volts. Now our voltage is correct. Doesn't matter what I turn this up to. Well, if I crank it right up, it'll shut down probably, but at 105 volts, let's see what happens here. 125 volts. I was looking at my my variac here. We'll see what voltage we're going to put into this thing and see whether it will shut down. So we'll turn on our power here. Okay, 125 volts going in. I've got 113 volts. My regulation is working now, right? And our normal voltage here is 120. So let's see how high I can go on this thing before it actually shuts down. The regulator will only work to a certain degree because it is a shunt regulator. So if I get beyond the control ability of the transistor here, the voltage is going to go too high and it is going to shut down. So it looks like it just did. It just did shut down because I see that the voltage has gone way up here. So I was just over 125 volts when it shut down there, which is fine because we don't have it's not designed to run on 125 volts. It's designed to run on 120. So we're at 113 volts now. Picture is on. And we're running at 125 from here. If I take this down to 120, so I find that at 120 volts we're fine. If I crank the voltage up, it's going to see how high I go before the set actually shuts down. So I'm increasing the voltage now. Still holding at 100. Okay, it shut down now. It's at about 130, 110, 100, yeah, about 130 volts. It's where, if we look at the variac here, it's got a voltmeter on it. As you can see, 130 volts, that's where the set went into shutdown. If I take it back down to 120 volts here, and power cycle it because the set has to reset, we'll see whether the set shuts down at this. I think we may have a capacitor that might be drying up in this regulation circuit, and it's just becoming a little sensitive, but we'll see if it shuts down. So it's going to see if it, we'll let it run here, just see if it hangs in at this voltage and doesn't kick out on me. But then I'm going to check for bad caps because I think I have a bad screen cap on here. I've got drive lines on the picture. Okay, running at 120 volts input. 15 minutes later, the TV's still running, the monitor's still running. I only call it a TV because it's not a TV, it's a monitor. It's holding solid, regulation's working on here. So that's problem number one taken care of. I think it probably was just dirt, oxidization on the control. And it wasn't, I cleaned it, I put some Neutral on there and give it a few turns, and now it's settling down and it's holding the voltage. Now we have to find the problem with the screen voltage. We have a screen capacitor, I think, that's gone bad on here because we've got a washed out picture with retrace lines. on it, which typically means the screen voltage is too low. Let's check the screen voltage. Our screen voltage is what drives the cathodes for the guns on the picture tube. Normally about 150 volts is what you should find if there's no picture at all. I'm only coming up at about 107 volts here. So most certainly we have a capacitor that's gone bad in the screen circuit. So now it's just a point of tracing it back. It's going to probably be one of these ones down in here, you know, for off the flyback. The screen voltage is derived off of a winding on the flyback transformer. Typically just a half-wave single diode rectifier, and it's going to be, you know, something small, probably 10 microfarad, 250 volt is more than likely what I'm going to be looking for here. A word of caution too, if you're working on a CRT set, there are some exceptionally high voltages in around the picture tube here. You've got your master screen volts, which is typically a couple thousand volts. Your focus voltage is typically around 10,000 volts. That's on these big thick leads here, so, and they'll go to the screen bleeder resistor and the focus bleeder resistor box here. So you want to be careful when you're sticking your fingers around here that the set is turned off. You don't want to be poking around here with the set powered up. One of my screen drive for my video is going to be probably one of these wires here. Just looking to see which ones go to the video circuits. Okay, it's probably this blue wire here I'm looking at. This blue wire, no, that's a heater. I'm just looking at the markings here. That's a heater line. So it's not the blue wire. So it's more than likely going to be this gray wire over here that goes down here. And it should be common to all the cathodes, or all the collectors, sorry. Yeah, I think that might be the one. See where it goes on the main board. Some more light on here so I can see. Screen wire looks to be the orange wire from here, and that goes down over towards the middle of the board. So this is going to be a fun one to get at. Yeah, gotta figure out where it goes, but it appears to go right down to about the middle of the board. Maybe not. It's going to take out some wire ties here. Let's see if I can. This big shield doesn't make things any easier to work on, I tell you. Okay. Okay, looks like it goes right down to about there on the board. So we're going to power this setup with my color bar generator, and I can see I'm way off frequency. On the back of this set there is a horizontal hold control, so I'm just going to turn the horizontal hold control and see if that'll bring my picture back. So horizontal hold. There we go. We are in sync. Now let's just check our color off here. Gonna turn off the color completely. Oh, these controls are all dirty. We'll set our brightness and our contrast. I think we need to clean these controls. Okay, we're going to use the service mode. There's a switch on the back marked service. If I flip the service switch, it'll kill my vertical and give me just a straight line across the screen. Now I can use this to adjust my white balance accordingly, because the picture is looking kind of green in this picture. So I'm just going to turn everything down to minimum. And I'm going to use the screen adjust controls on the back to adjust for a white line. So I've got 3 screen and 2 drive. So what we do is we adjust each one. We turn them all down to minimum first. Probably wouldn't hurt to clean these controls too, because I'm sure they're probably just as dirty as everything else on this set. And we adjust each one So we just see our blue line and our green line and our red line. So now we've got a white picture, a black and white picture. If I restore my vertical, as I turn up my brightness and my contrast, I should have a picture that's tracking relatively well for my white to black ratio. I still got to clean these controls here. They're still filthy, but I haven't got into there yet to clean them. Now I set the control to the mid position. I'm going to adjust my master brightness. Should be a master brightness control on here. It's my main screen, I believe, is what I'm looking for. And we're going to adjust so that our darkest bar is, but we don't want to be blooming over here, right? So we want to adjust our bias so that our tube is just biased on. We're going to adjust our balance again here to give us a white picture, a white line. After adjustment, this set doesn't look too bad. The color level's a little bit on the hot side there, but totally acceptable. Tint, like that cyan bar, just a little more cyan. It's not too bad. It's got a few more adjustments to make on here to get my color balance looking good. We can also adjust our vertical height so that we can just barely scan to the edge of the picture without over scanning, like that. As you can see, our 116 volts regulator is working. The regulator is now locked in at 115.7. The picture is not shutting down. I think probably why it was going into shutdown mode was because the horizontal oscillator was off frequency. And with the horizontal oscillator off frequency as far as it was driving the high voltage way up. So now that the oscillator is set correctly, controls have now been cleaned a bit. And where's my color control here? We can put our color bars back on here. This TV is actually, this monitor is actually not looking too bad. It's funny because the cameras, the color bars look absolutely perfect. I guess they look okay on camera there too. It looks different. It looks different on the LCD screen on the camera than what I'm looking at. But the bars look perfect right here. Color bars look perfect. I'll play some video on this thing. We'll see how this thing looks playing video. Color bars from that generator are totally different than off the tape. Wow, what a difference. Okay, play. Let's see how my little tape plays here. I got light shining on the screen here too, which doesn't help matters. Okay, this is an old Tape Life demo tape that I did years and years ago. I haven't seen this thing in forever.
So you bought yourself that new video camera. The pictures do look great. But how long will the videotape last? It's one of the touchiest questions in video, and few people bothered to ask it. How long does a video cassette last? Most of us operate on the assumption that the
Where's my
tape
brightness
records
on this
tape
thing?
will play back far into the future. But how long can we expect that tape to reliably store and recall our memories? The answer is not found in advertisements for videotape. But the truth
on
is,
the dark side here.
unfortunately, the
See
videotape
if we
is
can
not
bring this up a
forever.
bit.
Unlike movie film, which can last for decades, videotape is far more fragile. In fact, no magnetic recording medium is permanent. But now, thanks to an internal study by Sony in Japan, a tape manufacturer has gone on the record with a specific estimate on the life of its videotape products that should shatter any illusion that video is forever. The Sony report concluded that the life expectancy of any tape depends on disintegration of its chemical components.
Well,
such
I
as
haven't seen
plastic,
this.
base film,
I haven't seen this in years. This is one of my commercial videos I did years ago for my company.
Heat and moisture accelerate the breakdown of these organic materials in all tape formulations. The tape you're looking at now is a 15-year-old Sony Betamax tape. It was recorded in 1984 and was stored in a drawer. It has not been played since it was recorded and is now no longer playable. As you can clearly see, the oxide coating is very clearly coming off this tape. Any attempt to play this tape would result in immediate contamination of the video heads on the playback machine. The video on this tape, unfortunately, is now lost forever. For important, irreplaceable tapes, the ultimate in protection is to have the videotapes transferred to a DVD or a video CD. DVD archiving is available, but at a cost well above what most consumers are capable of.
You can tell this is really, really
The
old.
alternative is the video CD. A video CD is
Very
a
old.
compact
This
digital video disc.
this video
It
is.
played back on most DVD players.
This is long before DVD
or
recording
DVD-ROM.
became affordable. This is back in the day when DVD-R discs were around $20 to $30 for a blank disc.
Video CD.
So, my machine just shut down on me. The power switch needs to be cleaned on this thing again. This player has been sitting. It's been sitting without being used. And what happens is the power switch.
is slightly better than VHS and provides long-term storage with no wear and tear from repeated playbacks. The procedure to create a video CD is quite simple. First, the videotape is played back and digitized by a professional quality capture board onto the computer's hard drive. After capture, the video may be edited first or simply passed directly into the MPEG-1 encoding program. Once the video clips are encoded, they are then assembled in sequence into the VCD burning software and transferred to either a CDR or a CDRW disc. The media used will depend on the compatibility of the DVD player in question. Not all current players support CDR media, but most do support CDRW media. After recording, the CD is tested for compatibility on our studio DVD player.
It looks like that tape is shot. Look at this. That's a digital tape. Wow. That's what happens to DV tapes after they've been sitting for a while. I can tell you, I remember roughly when I made that recording because that's my daughter and she's only about 2 at that, maybe 1.5 at the time when this video was made. So that would put this around 1998, 99, I guess, is when I recorded this. I wonder if there's a date. Yeah, this actual tape was recorded. You can see when I made the recording. This video was put together in 2001. That was when this particular promo tape that I was doing for my company way back in 2001 when I was first into the archiving business. It just shows that tape here that I'm playing on my little video player here, it's starting to deteriorate because it started to contaminate the heads as I was playing it. That's the problem with videotapes. Anyway, this monitor is fixed. It's looking good. Back on the bar generator here. Just got to put the set back together, and then we'll get this one up on the shelf for use in my as my studio test monitor. Thanks for watching. We'll catch you in the next one. Bye.